Welcome to the AI Research Roundup. I'm Alex. Today we are looking at a paper from the Hugging Face trending list, published on September 18th, 2025, just yesterday. The standout result is a simple two-stage recipe that lets robots self-improve using their own steps-to-go estimates, delivering large sample-efficient gains, like raising success from about 45% to 75%, with only around 3% extra practice in one setting. The paper is titled, Self-Improving Embodied Foundation Models, and as we will see later, the implications for model training are quite significant. The method combines supervised fine-tuning with a self-improvement stage that uses the learned steps to go for reward shaping and success detection, enabling autonomous skill acquisition. On X, reactions highlight the two-stage recipe, noting supervised fine-tuning plus online reinforcement learning with self-predicted rewards, the 45% to 75% jump with about 10% robot time, and autonomous skill acquisition beyond imitation data. Engagement looks moderate, with roughly 115 likes. Alright, the previous segment highlighted the two-stage recipe and why it matters. Figure 1 lays out the pipeline. On the left, a pre-trained multimodal model feeds into stage 1, where supervised fine-tuning uses both behavioral cloning and a steps-to-go prediction objective. The right panel shows stage 2, where online rollouts use the steps-to-go signals to create rewards and a success detector, so robots can practice with light human monitoring. The bottom flow indicates self-improvement reward labeling and reinforcement learning that update the policy. So the previous figure outlined the overall pipeline. Figure 2 illustrates how steps-to-go behaves during a single Aloha insertion episode, which grounds the reward shaping idea. The top image strip shows key moments, while the lower plot tracks expected steps to go over time. The curve rises when the robot drops or misgrasps the peg, and it falls when the pose improves and insertion progresses, so the shaped reward becomes positive for helpful motions and negative for setbacks. This alignment explains why on-policy reinforcement learning stays stable. So the previous figure grounded the reward signal in one episode. Figure 5 presents the headline results across 5 settings, with orange points for supervised policies and blue points for self-improvement. The panels show consistent jumps in success rate with only a small number of extra episodes, which means strong sample efficiency. The banana table panel illustrates rapid generalization, rising from about 63% to around 85% within 8 hours. So, the previous figure summarized broad gains across tasks. Figure 8 shows why multimodal pretraining matters for self-improvement. The left bars compare reward label sources across dataset sizes, and the blue Pally reward consistently tops green UniPally and red Scratch, which is most pronounced at 10 and 20% data. The right curve tracks success during self-improvement, and the Pally reward climbs faster and surpasses the dashed baseline, while UniPally lags. This gap implies better reward shaping because the jointly pre-trained vision language model estimates steps to go more reliably. Alright. The previous figure contrasted Pally and UniPally rewards. Figure 9 shows strong generalization on banana table, with top image strips depicting struggles before stage 2 and bottom strips showing smoother, straighter pushes after stage 2 because the policy learned strategies that reduce rotation. The side panels compare language table and banana table robot views, which emphasizes that the objects and visuals differ. The key message is rapid skill acquisition. The robot adapts to a novel banana object and executes directed pushes more reliably. Okay, 2 takeaways stand out. Steps2Go turns a pre-trained vision language model into its own reward and success oracle, so online reinforcement learning becomes stable and sample efficient, and pairing that with web-scale pre-training unlocks fast generalization to new objects. The broader implication is practical, lightly supervised robot self-practice. That is it for this episode of AI Research Roundup. I am Alex. Thanks for listening.